After learning how to draw a bending moment diagram by parts, we learn how to calculate deflection of beams by double integration method. To find the deflection of beam by double integration method, we need to develop a fundamental relationship between moment and curvature of the beam. This is called moment-curvature relationship. To develop this moment-curvature relationship, we have to consider three assumptions. The beam material follows Hooke's law. The deflection and the slope are small at every point of the deflection curve, and the deflection due to shear force can be neglected. In the derivation of flexural formula, chapter 14 of your text, the radius of curvature of a beam is given as 1 divided by rho equals to m divided by EI. This 1 divided by rho equals to m divided by EI. This formula you can get by combining equation 14.2 and equation 14.5 of your text. In this expression, 1 by rho is known as curvature, m is the internal moment, EI is the flexural rigidity of the beam and it is always positive. E is material property, it depends on the material types. I is the cross-sectional property. In calculus, the radius of curvature of a curve can be given by this expression. Therefore, by approximation, we can write 1 divided by rho equals to d square y divided by dx square. As this value, we can take as 1. So our fundamental relationship between moment and curvature is d square y divided by dx square equals to m divided by EI. If we integrate this equation once, we will get dy by dx, which is known as slope of the elastic curve. If we integrate this equation 2 times, then we'll get y value, which is the deflection of the curve. To apply this, we will integrate this one. Constant of integration will come in the expression. To calculate the constant of integration, we need to apply the boundary condition. What are the boundary conditions? At any support, either it is roller support, pin support, or fixed support, the deflection will be 0. That means y equals to 0 or delta equals to 0. If it is external roller, then deflection is 0. If it is internal roller, deflection is 0. If it is external hinge, deflection is 0. If it is internal hinge, deflection is 0. If it is a fixed support, then not only the deflection is 0, slope will be equals to 0 and deflection will be equals to 0. If it is a free end beam, for free end, the boundary condition V equals to 0, shear equals to 0 and moment equals to 0. For internal hinge or internal pin, the boundary condition will be moment equals to 0. This boundary condition will be helpful in calculating the constant of integration. We'll see one example. This is example 1. This is a cantilever beam. It is subjected to a point load at the free end of the beam. We can see if we put this type of load, maximum deflection will occur here at the end of the beam. We have to calculate that maximum deflection. To calculate this maximum deflection, we have to calculate the equation of elastic curve. To get the equation of elastic curve, we have to find one moment expression at any distance x. To find the moment expression at any distance x, we have to cut the beam at any distance x. When we'll cut this beam, we can find this moment equals to minus px. Then if we insert this one in our expression, which we developed earlier, ei d square y divided by dx square equals to minus m is minus px. That means negative moment here. This is our expression, moment curvature relationship. Now, if we integrate one time, then we can write ei d delta divided by dx minus px square divided by 2 plus c1. This is constant of integration. This one is the slope equation, equation number 2. If we integrate again, we'll get ei delta minus px cubed divided by 6 plus c1x plus c2. There are two constant of integration is there, c1 and c2. This is equation number 3, and this is the equation for the elastic curve. That means if we get this equation at any distance x, we can find the delta or y, that is the deflection of the beam. As we have two constant of integration, c1 and c2, we need two boundary conditions. We can see from the beam that the beam is supported at the end and it is a fixed support. So we have two boundary conditions. At fixed support, as we know, we have two boundary conditions, deflection equals to 0 and slope equals to 0. So we can write at x equals to L, slope equals to 0, dy divided by dx or d delta divided by dx equals to 0. Similarly, at x equals to L, delta equals to 0. If we apply these two boundary conditions from equation 2 and 3, we can get c1 and c2 value, and this c1 value will be pl square divided by 2 and c2 equals to minus pl cube divided by 3. If we put this c1 and c2 in equation number 3, we'll get the expression for delta is this one. This is called equation of the elastic curve. Now, if we put any x value, we'll find the corresponding deflection. As we know that our maximum deflection will occur at x equals to 0. So when we'll put x equals to 0, we'll get the deflection at point A is minus PL cubed divided by 3EI, and the slope at point A, theta means dy by dx or d delta by dx, is PL squared divided by 2EI. The integration method provides a convenient method for determining the slope and deflection equations if the moment is a continuous function of x. Generally, on a beam, there will be multiple loads and various types of load. In that case, you have to write separate moment equation for each section of the beam. Thus, this method, integration method, requires a lengthy calculation. We need to write one single moment equation for the whole beam with complex loading. To help with this, we have to introduce one function that is known as singularity function. The function are shown in table 15.2 of your text. In general form, the function is like this. It is written using pointed bracket. X minus a to the power n equals to 0. When x minus a is negative, that means x is less than a, it will be equals to 0. When x is greater than a, that means x minus a is positive, then this pointed bracket will act as normal bracket. The normal integration law you can apply to the singularity function. as it is pointed bracket, but when you apply the integration, it will be n plus 1 plus constant of integration. You can use this table to write the moment expression. If it is subjected to one moment, the moment expression will be like this. If it is subjected to point load, the moment expression will be like this. If it is subjected to uniformly distributed load, the moment expression will be like this. If it is a triangular variation of load, the moment expression will be like this.